Hi, thanks for joining me today. I've got a two-part problem involving powers of 3. For part 1, we have a set S, which is a subset of the positive integers, with the size of S being n, which is at least 3. We're going to define this set here, Ls, to be the set of S1 plus S2 plus S3, where S1, S2 and S3 are all in S and are distinct. So Ls is simply the number, or the numbers which can be written as the sum of 3 distinct elements of S. For part 1, we want to prove that the number of powers of 3 in Ls is at most n minus 2. So we look at the set Ls and count however many powers of 3 there are in Ls, and it should be at most n minus 2. That's part 1, and then for part 2, we essentially want to find an S which attains this bound. So we fix n a positive integer at least 3, and we want to find an S such that Ls contains exactly n minus 2 powers of 3. Okay, if you want to have a go at this problem, pause the video now and give it a go for yourself. I'm going to jump straight into the solution. Okay, so for part 1, we're just going to use induction on n. So let's look at the base case where n equals 3, so S just contains 3 elements. So this is the base case, n equals 3, and we're going to have S just has 3 elements, so it's of the form S1, S2, S3. Well then Ls is simply just going to be the set with just one element in, namely S1 plus S2 plus S3, whatever that number is. And either that's a power of 3 or it's not, it doesn't really matter, but n minus 2 in this case is just 3 minus 2, which of course is 1, and clearly this set here is going to contain at most 1 power of 3. Again, this is either a power of 3 or it isn't. So certainly the base case is satisfied, and of course we've got to proceed by induction. So now let S just be an arbitrary set with, arbitrary subset of the positive integers with n elements, where n is at least 4 now, and then we're going to assume it holds true for n minus 1, and then show it's true for this n as well. So S, we're going to just write out as S1 plus S2 plus so on, all the way up to Sn, and without loss of generality, S1 is less than S2 is less than, and so on is less than Sn. Now, essentially what we want to do is notice that if we take Sn as being one of the things that we have 3 terms that we're going to add up. If we let Sn be one of them, so we've got Sn plus, say, Si plus Sj, where 1 is, say, less than or equal to I, is less than j, is less than or equal to n minus 1, because these guys all have to be distinct. This guy here, well, what do we know? It's going to be strictly bigger than Sn, but it's also going to be strictly less than 3 times Sn, because this guy here is Sn, this is less than Sn, this is less than Sn as well. So all in all, this is less than 3Sn, but it's clearly bigger than Sn. Okay, but in this range here, and this holds for all I and j which satisfy this guy here, so if we take any 2 elements from this guy here, but notice this range here is some number, Sn, and then 3 times that number. Hence, in this range here, so in the kind of interval, Sn, or maybe I should put open interval, Sn, 3Sn, there can only be 1 power of 3. There can't be 2 powers of 3, it just wouldn't work. There's not enough space to fit them in, because if there was a number in here, let's say lambda, which was a power of 3, so lambda, let's say, is bigger than Sn, but less than 3Sn, well then 3 lambda very clearly is going to be bigger than 3Sn, so it's not going to be in this range here. So there's at most 1 power of 3 in this range here, and hence this guy here can only ever be at most 1 power of 3. Hence, when we take 3 kind of elements from this set here, if one of them is Sn and we're adding them up, there's only 1 power of 3 it could possibly be. Hence, when we look at Sn and include that in our kind of 3-way sum, it's only ever going to contribute at most 1 power of 3 to Ls. So that means the size of Ls, or if I perhaps define S tilde to be S1 all the way up to Sn minus 1 now, then the cardinality of Ls, this guy here, is going to be at most 1 plus the cardinality of Ls tilde. Okay? And the reason for that is, if I take any 3 from this guy here and add them up, of course that's going to be in this set here Ls tilde, and the only way I'm going to get stuff in ls which isn't an ls tilde is if I include Sn, but as I say, there's only one power of 3 that could possibly be. So, in fact, I don't mean this. I should probably say the number of powers of 3. So ls intersect, let's say k. So k is going to be the set of powers of 3. So 3, 9, 27, and so on. Okay, so ls intersect k is less than or equal to 1 plus ls tilde intersect k. But by assumption, this guy here is going to be less than or equal to n minus 1 minus 2. So this is less than or equal to 1 plus n minus 1 minus 2. And of course, it is just n minus 2. And that gives us our result by induction. So that solves part 1. Let me clean up the whiteboard and we'll move on to part 2. Okay, so for part 2, we just want to find an S that attains this bound. So S has n elements, and ls intersect the powers of 3 is exactly n minus 2. Now, if you just have a think about this, you could probably come up with an example yourself, but the example I'm going to give is hopefully pretty straightforward. It's simply going to be S equals 1, 2, then 3 squared minus 3, 3 cubed minus 3, and so on, all the way up to 3 to the n minus 1 plus minus 3. Like so. How many elements does this set S have? Well, it's got n minus 2 kind of 3 to the k's minus 3, so in terms of that form there, and then plus 1 plus 2. So n minus 2 plus 2, so it certainly has n elements. And well, what is ls intersect k? Well, notice that ls is certainly going to contain all of these guys here. Well, 1 plus 2 is 3, and then if I add that onto this third term here, 3 squared minus 3, that's going to give me 3 squared. Similarly, 1 plus 2 plus 3 cubed minus 3 is going to give me 3 cubed, and so on, all the way up to 3 to the n minus 1. And of course, all of these guys here are distinct. And yeah, I guess I should have made comment up here, all of these elements here are distinct. 1 is less than 2, 2 is less than 7, which is 3 squared minus 3, and clearly this term is going to be less than that term less than that term, and so on. Okay, and I guess that's why we started at 2 instead of 1 up here. If we started with 1, we would have just got 3 minus 3, and that would have given us 0, which would contradict the fact that S has to be a subset of the positive integers. Anyway, ls certainly contains all these elements here, so certainly ls is going to be bigger than or equal to, and notice that all of these guys here are powers of 3, so ls intersect k is certainly going to be bigger than or equal to the size of this set here, which is just n minus 2. But from the argument we just had, ls intersect k must be at most n minus 2, and therefore ls intersect k is exactly n minus 2. And that solves part 2. I hope that has all made sense, and I hope you have enjoyed this fun problem involving powers of 3. Thank you for watching. I'll catch you in the next one. Have a great day.